Okay, let's get into it. Number 12. The faint young sun. Picture the sun about 4 billion years ago. Same star, roughly the same place in the sky, but dimmer, not a little dimmer, about 30% dimmer. A pale, weaker version of the star we know. Now run the numbers, the way astronomers first did back in 1972. A young sun putting out only about 70% of today's energy should have left the early Earth frozen solid, a white ball of ice from pole to pole for hundreds of millions of years. No open oceans, no warm shallow seas, nothing for life to get started in. And yet, when we read the rocks from that exact period, we find the opposite. We find liquid water. We find riverbeds and lake sediments. We find the chemical fingerprints of living things, going back almost as far as the rocks themselves. The planet wasn't frozen. It was wet, and it was alive. Two astronomers, Carl Sagan and George Mullen, laid this contradiction out plainly, and it's been nagging at scientists ever since. They called it the faint young sun paradox. Their first idea was that a thick blanket of ammonia in the air trapped enough heat to keep things warm. That turned out not to work. Sunlight tears ammonia apart in no time. So the explanation shifted to other greenhouse gases, more carbon dioxide, maybe methane pumped out by early microbes, a thicker atmospheric blanket doing the work the weak sun couldn't. And here's the thing. That explanation probably is the answer, at least in broad strokes. This isn't magic. But look at what it demands. The sun has been slowly brightening this entire time, and it still is. So to keep Earth's temperature in the narrow band where liquid water survives, the greenhouse had to fade at almost exactly the rate the sun brightened. Too much greenhouse as the sun got stronger, and you cook the planet. Too little back at the start, and you freeze it. Somehow, over 4 billion years, Earth threaded that needle. Scientists sometimes talk about this as if the planet had a thermostat, a set of feedback loops that nudged the temperature back toward livable every time it drifted. Maybe that's true. But a thermostat that holds steady for 4 billion years, through a sun that keeps turning up the heat, is a remarkable thing to just be handed. The record is clear that it happened. We're standing on the proof. The question that lingers is how tight that margin really was, and how many worlds out there got the same weak young star, and simply froze, and stayed frozen, and never woke up. We didn't. And for the first billion years of that, the sun was too faint to explain why. Number 11. Jupiter's shield. There's a comforting story you've probably heard. Jupiter, the giant of the solar system, sits out there like a bodyguard. Its gravity is so enormous that it grabs incoming comets and asteroids, swallows them or flings them away, and keeps the inner planets safe. Earth included. The big brother taking the hits so we don't have to. You can even point to the moment that story felt true. In 1994, a comet called Shoemaker-Levy 9 broke into pieces and slammed into Jupiter one fragment at a time, leaving bruises in the cloud tops bigger than our entire planet. We watched it happen. Better Jupiter than us, right? But then two scientists, Jonathan Horner and Barry Jones, decided to actually test the bodyguard story. Not assume it. Test it. They ran simulation after simulation, changing the mass of the planet sitting in Jupiter's orbit, and counting how many objects ended up hitting Earth. They called the project, quite fairly, Jupiter, friend or foe. The answer they got was not the comforting one. For long-period comets, the ones that come screaming in from the deep freeze of the outer solar system, yes, Jupiter genuinely does help. It shields us. But those comets are only a few % of the things that threaten Earth. For asteroids, the far more common threat, the picture flipped. A giant planet actually stirs the asteroid belt, kicking rocks onto paths that cross ours. In their models, the impact rate on Earth peaked when the planet in Jupiter's spot was about 1/5 of Jupiter's real mass. So Jupiter isn't a simple shield. It's more like a bouncer who keeps some troublemakers out and accidentally shoves others straight toward you. But here's the part that fits tonight's theme. Horner and Jones found that if Jupiter were half the mass it actually is, Earth would be a far more dangerous place. And if there were no Jupiter at all, the impact rate would be roughly what we have now. Our actual Jupiter, at its actual mass, in its actual orbit, sits at a spot that gave Earth a survivable pounding, not zero impacts. We've had plenty, but not so many, so often, that life kept getting knocked back to zero. Change that one planet's mass, and you change the entire history of collisions that shaped this world. The asteroid that ended the dinosaurs and cleared the way for us was part of that history. So was every impact that didn't happen because the timing was slightly off. Jupiter didn't tuck us in at night, but the specific giant we ended up with helped set the rhythm of catastrophe on Earth. A little different, and that rhythm gets faster. And a faster rhythm is one where nothing complex ever gets the time to grow. Number 10. The moon's grip. Look up at the moon and you probably think of tides. Maybe eclipses. Maybe just something pretty to look at. What you probably don't think is that it's the reason you have stable seasons at all. Here's the situation. Earth spins on a tilted axis, leaning over by about 23.5 degrees. That tilt is why we have summer and winter. It's fixed enough that the seasons come around like clockwork, year after year, for as long as anyone or anything has been alive to notice. But that stability is not automatic. The other planets are constantly tugging on Earth with their gravity, and left alone, those tugs would make our tilt wander, not smoothly, chaotically, lurching from one value to another over millions of years in ways you can't predict. In 1993, a French scientist named Jacques Lasker and his colleagues worked out just how bad it would be. With the moon present, Earth's tilt stays locked in a tiny range, wobbling only about 1 degree either side of where it sits now. Rock steady. But take the moon away, and the calculations explode. The tilt could swing anywhere from nearly 0 degrees all the way to 85 degrees, almost lying on its side. Think about what that means for the surface. At a high tilt, the poles cook and the equator freezes. Whole continents would swing between scorching and glacial over timescales far too fast for complex life to adapt. You don't build rainforests and coral reefs and civilizations on a planet whose seasons reinvent themselves every few million years. The moon prevents all of that. It's massive enough and close enough to act like a gyroscope, holding our spin steady against everything the other planets throw at us. And our moon is strange in this respect. Compared to the planet it orbits, it's enormous. Most moons are tiny specks next to their worlds. Ours is a genuine companion, more than a quarter of Earth's width. That size is exactly what makes it a good anchor. Now, science being science, there's a wrinkle. A later study in 2011 ran the moonless Earth numbers again, and argued the swings might be a bit less violent than Lasker first suggested. Survivable, maybe, for some kinds of life. So this isn't a closed case, but even the gentler version agrees on the core point. Without the moon, our climate would be a far shakier, far less predictable thing. And here's the quiet twist. The moon is leaving. Every year it drifts about 3.5 centimeters farther away. Slowly, over enormous stretches of time, its grip on our tilt will loosen. The anchor is being reeled out. For now, though, it holds. Every steady season you've ever lived through, every reliable harvest in human history, rests partly on a giant rock that happened to end up in orbit around us, doing a job it doesn't know it's doing. Take it away, and the sky itself would start to wander. Number 9. The impossible collision. So where did that improbably large moon come from? The answer is one of the most violent origin stories in the solar system, and it's a story where the details had to fall almost perfectly into place. Rewind to about 4.5 billion years ago. The early Earth is young, molten, still forming, and it is not alone. The inner solar system is crowded with other growing worlds, and one of them, roughly the size of Mars, is on a collision course. Scientists have given it a name, Theia. Theia hits us, but how it hits matters enormously. Come in too fast, too head-on, and you don't get a moon. You get 2 planets shattered into rubble, or 1 planet vaporized entirely. Come in too gently and glancing, and Theia just skips off or merges quietly, leaving no moon at all. What actually happened, according to the leading models, was a strike at a low, oblique angle, at a relatively modest speed, close to the point where the 2 worlds were just barely gravitationally falling into each other. That specific kind of hit blasted a huge amount of molten rock into orbit without destroying the Earth. And out of that ring of debris, over a surprisingly short time, the moon pulled itself together. The evidence for this is genuinely good. The angular momentum of the Earth and moon spinning around together points to a big collision. The moon has only a tiny iron core, which fits because the debris came from the outer rocky layers, not the metal heart of either world. And the moon shows signs of having once been molten to great depth. Exactly what you'd expect from material, flung out white hot. But here's the detail that still keeps scientists up at night. When you measure the oxygen in Earth rocks and moon rocks, the isotopes, the different weights of oxygen atoms, match almost perfectly. Nearly identical. And that's strange. Theia was a separate world, formed somewhere else, presumably with its own distinct chemistry. So why does the moon, supposedly built mostly from Theia, carry Earth's exact fingerprint? That single question has spawned a whole family of competing models. Maybe the impact was more energetic, mixing the 2 bodies so thoroughly they became chemically identical. Maybe Earth briefly became a spinning cloud of vaporized rock, a shape called a synestia, that condensed back into a planet and a moon. The arguments are still going. What nobody argues about is the tightrope. A world the size of Mars hit us hard enough to make a moon, and gentle enough not to erase us. Faster, and there's no Earth to stand on. Slower, and there's no moon to steady the sky. We got the one collision, out of countless possible collisions, that built the exact companion we needed. And it happened before there was anyone here to be lucky about it. Number 8. Earth's magnetic shield. Deep under your feet, about 3,000 kilometers down, there is an ocean of liquid iron. It's hotter than the surface of the sun, and it's moving, churning in slow, enormous currents. And that churning does something you can't see, but absolutely depend on. It generates Earth's magnetic field. That field reaches far out into space, wrapping the whole planet in an invisible shell. And its job is to stand between you and the sun. Because the sun isn't just pouring out light. It's blowing out a constant stream of charged particles, the solar wind, moving at hundreds of kilometers a second. Left unchecked, that wind would strip a planet's atmosphere away, molecule by molecule, and fling it into space. Our magnetic field deflects most of it. The solar wind hits the shell, slides around it, and streams off past us. The air stays put. The oceans stay put. Life goes on, mostly unaware there's a war being fought over its head. Now, if you want to know what happens to a planet that loses this protection, you don't have to imagine. You can just look at Mars. Mars, we now know, once had all of this. A magnetic field, a thick atmosphere, rivers that carved valleys, lakes, maybe even a shallow ocean. For a while, it may have been a second living world, right next door. But Mars is small, much smaller than Earth, and small worlds cool down faster. About 4 billion years ago, the churning iron core of Mars slowed, and its dynamo shut down. The magnetic field faded. The shield dropped. and then the solar wind went to work. Over hundreds of millions of years, it stripped the Martian atmosphere away into space. The pressure fell. The water boiled off or froze into the ground. The rivers stopped. And Mars became the cold, dry, silent desert we send our robots to today. We're not guessing about this. NASA sent a spacecraft called MAVEN specifically to watch it happen. And MAVEN found that Mars is still losing its air right now, bleeding roughly 100 grams of atmosphere into space every second. Back when the young sun was more violent, that loss would have been hundreds of times faster. So here are two rocky planets, formed at the same time, from the same material, next door to each other. One kept its molten heart spinning and held on to its shield, its air, its water, and its life. The other lost the spin, lost the shield, and died. The difference wasn't distance from the sun. It was size, and a churning core, and a magnetic field we happen to keep. Mars is what Earth looks like with the shield down. A preview of a version of us that couldn't hold on. And when you stand outside on a clear night, that quiet magnetic shell is still up there, still bending the solar wind around you, doing the one thing that keeps this planet from going the way of the red one next door. Number 7. The Galactic Habitable Zone. You've probably heard of the habitable zone around a star. The narrow band, not too hot, not too cold, where a planet can hold liquid water. Earth sits comfortably inside the suns. But zoom way out, past the planets, past the sun entirely, and ask a bigger question. Is there a habitable zone around the whole galaxy? A lot of astronomers think there is. In 2004, a team led by Charles Lineweaver mapped it out for the Milky Way. And what they found is that where you sit inside a galaxy matters just as much as where you sit around a star. Think about our galaxy as a giant spinning disk. Right at the center, near the crowded core, it's a dangerous neighborhood. Stars are packed close together. Supernovae go off often. There's radiation and gravitational chaos, and the occasional roar from the giant black hole at the center. A planet there gets sterilized before life has a chance to find its feet. Go too far out toward the edge, and you hit the opposite problem. Out there, the raw material runs thin. To build a rocky planet like Earth, you need heavy elements, forged inside earlier generations of stars. Astronomers call the abundance of those elements metallicity, and in the outer galaxy, the metallicity drops so low that Earth-like planets can barely form at all. So the sweet spot is a ring in between. Lineweaver's team put it roughly 7 to 9 kiloparsecs out from the center, far enough from the core to be safe, rich enough in heavy elements to build worlds. And our solar system sits right inside that ring. We're in the quiet suburbs, between the dangerous downtown and the barren outskirts. But the part I find most striking is that this zone isn't just about place. It's about time. Lineweaver's team argued that complex life could only really get going in a specific window of galactic history. Too early, and the galaxy was a violent place, still lighting up with supernovae and short on the elements life needs. Come along at the wrong epoch, and even the right address won't save you. Now, this idea has its critics. Later studies argued the safe zone might be bigger, or blurrier, than that original neat ring, especially once you account for stars drifting inward and outward over billions of years. So don't take the boundaries as gospel. But the underlying point holds up. A galaxy is not uniformly friendly. Most of it is actively hostile to the slow, patient chemistry that life requires. We happen to live in the calm band, at a calm time, in a galaxy that spent billions of years becoming just barely capable of supporting us. Move our sun a few thousand light years inward, and the sky would be brighter, busier, and lethal. Move it outward, and there might not be enough of the right stuff to have made us in the first place. We are parked in the one part of the neighborhood where the lights are on and nothing's on fire. Number 6. The lonely sun. Here's something that sounds like it should be trivia, but turns out to matter a great deal. Our sun is alone. That feels normal to us because it's all we've ever known. One sun in the sky. But across the galaxy, that's not the default. A huge fraction of stars, especially the bigger, sun-like ones, come in pairs or larger groups. Binary systems. Triple systems. Stars locked in orbit around each other, circling for billions of years. In our own stellar neighborhood, the fraction of the more massive stars living in multiples runs up around 78%. Solitary stars like ours are, in that sense, the exception among their kind. And being in a pair is not a good setup if you're a planet trying to hold a stable orbit for the billions of years life seems to need. Picture a world trying to circle two suns at once. The gravity it feels is constantly shifting as the two stars swing around each other. Depending on the arrangement, that can stretch a planet's orbit into a long, lopsided ellipse, or heat it and freeze it as its distance to the stars keeps changing. In the worst cases, the gravitational tug-of-war becomes so chaotic that planets get flung out of the system entirely, cast into the dark. Physicists have a precise name for the mechanism, resonance overlap, but the upshot is simple. Two stars make for messy, unstable, hard-to-survive orbits. The sun spares us all of that. One steady star, one steady center of gravity, one smooth, nearly circular path that Earth has traced, calmly, for 4.5 billion years. No wild swings in heat, no sudden ejections, just the same reliable orbit, over and over, long enough for single cells to become forests and fish and us. And there's a strange footnote here. For a while, some scientists seriously wondered whether the sun did have a hidden companion after all. A dim, distant partner star, never seen, that occasionally swung close enough to rain comets down on Earth and trigger mass extinctions. They even gave it a name out of Greek mythology, Nemesis. It was a real hypothesis, taken seriously, hunted for with telescopes, and the hunt came up empty. Deep infrared surveys swept the sky and found nothing. No companion, no nemesis. The sun really is a loner. Which, tonight, is exactly the point. In a galaxy where so many stars are bound to a partner, and where those partnerships make stable planetary orbits so much harder, we ended up orbiting one calm, single star, all by itself. The loneliness of the sun is one of the quiet reasons we're here to call it lonely. Number 5. The carbon resonance. Now we go small. Very small. Down into the heart of a star, where the elements that make you are being forged. Because there's a step in that process that, by rights, almost shouldn't work. And the fact that it does is the reason carbon exists at all. And you, and every living thing you've ever met, are built on carbon. Here's the problem stars have to solve. Inside a star, you start with hydrogen, which fuses into helium. Fine. But to make carbon, you need to fuse 3 helium nuclei together. And you can't easily do that all at once. Getting 3 of them to collide at the same instant is far too rare. So nature does it in 2 steps. First, 2 helium nuclei stick together to make a nucleus called beryllium-8. The trouble is, beryllium-8 is absurdly unstable. It falls apart almost the moment it forms, in a tiny fraction of a second. So you have this vanishingly brief window in which a 3rd helium nucleus has to slam into the beryllium before it disintegrates. And on paper, that reaction is far too slow to make all the carbon we actually see in the universe. The math simply doesn't add up. There should be almost no carbon. In 1953, a physicist named Fred Hoyle looked at this and made a bold leap. He reasoned that since carbon clearly does exist, since he himself was made of it, there had to be something helping the reaction along. Specifically, he predicted that the carbon nucleus must have a special energy level, a resonance, tuned to almost exactly the combined energy of beryllium and helium. Like pushing a swing at just the right moment, that resonance would let the reaction happen far more often than it otherwise could. Hoyle predicted the exact energy this resonance should have before anyone had ever detected it, and then Willie Fowler's lab went looking and found it, right where Hoyle said it would be, at an energy of about 7.65 million electron volts. The prediction was correct, and here's the fine-tuning. That energy level sits in a narrow window. Nudge it up or down by a small amount, and the resonance falls out of tune. The swing gets pushed at the wrong moment, and the universe makes drastically less carbon, too little for the chemistry of life. In some versions, almost none at all. There's a lovely argument about what this means. Hoyle himself was so struck by it that he suggested the laws of physics looked, in his words, like they'd been deliberately arranged. Historians of science push back and say the story got a bit mythologized over the years, that his original reasoning was more technical than mystical. Fair enough. The philosophy is up for debate, but the physics isn't. Carbon exists because of a tiny, precisely placed rung on an energy ladder inside dying stars. Move that rung, and the cosmos goes carbon poor, and biology as we know it never gets its raw material. Every atom of carbon in your body passed through that narrow gate, and it was opened by the thinnest of margins. Number 4. The strong force. Let's go smaller still, to the force that holds the very center of every atom together. Physicists call it the strong nuclear force. It's the glue binding protons and neutrons into nuclei, and it is balanced on a knife edge so fine that it's genuinely hard to believe we're standing here talking about it. Here's the setup. Protons are positively charged, and like charges repel. So inside a nucleus, you've got protons that desperately want to fly apart, held together only because the strong force is even stronger than that repulsion, at very short range. Get the strength of that force right, and you get a universe full of stable nuclei, and hydrogen, and stars that burn slowly for billions of years. Get it wrong, even slightly, and everything falls apart. In two different, opposite ways. Go one direction first. Imagine the strong force were just a couple of % stronger. That sounds harmless. It isn't. With a slightly stronger glue, two protons could bind directly to each other, forming something called a diproton. In our universe, the diproton doesn't exist because the force isn't quite strong enough to hold two protons together against their repulsion. And that's a good thing. Because if diprotons were stable, then back in the first minutes after the Big Bang, hydrogen would have fused together almost instantly, wholesale, burning through the universe's hydrogen supply in a flash. And a universe with no hydrogen is a catastrophe for us. No hydrogen means no water, because water is two hydrogens and an oxygen. It means no long-lived stars like the sun, which run on slowly fusing hydrogen. It means no organic chemistry as we know it. A slightly stronger strong force, and you get a dead universe of helium and heavier elements with none of the light. Essential ingredient life is built around. Now go the other direction. Make the strong force a little weaker instead. Now it can't hold together even the simple building block called deuterium, a proton and a neutron stuck together. And deuterium is the very first step on the ladder of fusion. Stars build every heavier element by starting there. Knock out that first rung, and the whole ladder collapses. Stars can't fuse the way they do. The elements never get made, so the strong force is trapped between two disasters. Too strong, and you burn all the hydrogen away at the dawn of time. Too weak, and stars can't cook up the elements at all. The estimates for how much wiggle room there is vary, from just a couple of % up to maybe 10 or 15. But either way, it's a narrow ledge, and our universe is standing right on it. Some physicists argue the safe range is wider than the scary versions suggest, that life might find a way with different chemistry. That debate is real and worth having, but the basic shape of the thing is not in dispute. One of the four fundamental forces of nature is tuned to a value that permits both hydrogen and heavy elements to exist at the same time. Shift it, and you lose one or the other, and you need both to make a person. We got both, by a few percent. Number 3, matter over antimatter. This one is about the most basic question you can possibly ask. Why is there anything here at all? Not, why is there life? Or why is there Earth? Why is there any matter in the universe whatsoever? Because according to our best physics, there shouldn't be. Here's the trouble. When you make matter out of pure energy, and the early universe was doing exactly that on a colossal scale, you don't just make matter. You make matter and antimatter in equal amounts. For every particle and antiparticle, its perfect mirror opposite. And when a particle meets its antiparticle, they annihilate. They destroy each other completely and vanish in a flash of light. So run that forward. The Big Bang makes equal amounts of matter and antimatter. Everything meets its opposite. Everything annihilates. And you're left with a universe full of light and nothing else. No atoms, no stars, no galaxies, no planets, no us. A vast, glowing, empty nothing. That's what the equations say should have happened. And yet, here we are, made of matter, sitting on a whole planet of it, in a galaxy of it, in a universe absolutely full of the stuff. Somehow matter won. And when physicists worked out by how much it won, the answer was almost unbelievably delicate. In the early universe, for roughly every billion particles of antimatter, there were about 1,000,000,001 particles of matter. A 1 in a billion excess. Everything annihilated in matched pairs. 1,000,000,000 against 1,000,000,000. All of it flashing away into light. And that tiny leftover, that single extra particle in 1,000,000,000, is everything. Every star, every world, every atom in your body is part of that razor-thin surplus that didn't have an opposite to cancel it out. So the obvious question is, why the imbalance? Why 1,000,000,001 instead of a clean billion? Back in 1967, the physicist Andrei Sakharov laid out the conditions the universe would have to meet to tip the scales toward matter. It's a beautiful piece of reasoning. The problem is, when we go looking for those effects in our actual particle physics, they're there, but they're far too weak. We do see a tiny imbalance between matter and antimatter in certain particle decays, but it's nowhere near enough to explain a whole universe made of matter. In other words, we know it happened, because we exist. We just can't fully explain how. It's one of the great open problems in physics, and people are chasing it right now with particle accelerators and underground detectors, trying to catch nature in the act of favoring matter over its mirror. But sit with the strangeness of it for a second. The universe manufactured almost perfectly equal amounts of something, and its opposite, then let them wipe each other out. Almost completely. Almost. And in that almost, in that one part in 1,000,000,000 that survived the Great Cancellation, is everything that has ever existed. We are the rounding error of the early universe, the part that didn't get erased. Number 2, the orderly beginning. There's a law of physics you feel every single day, even if you've never named it. Things fall apart. Order decays into disorder. A hot coffee cools down. A sandcastle crumbles. A tidy room gets messy on its own, but never the reverse. Physicists call the measure of that disorder entropy, and the rule is that entropy always increases. The universe is always sliding, relentlessly, from order toward chaos. Now follow that logic backward in time. If disorder is always increasing, then the past must have been more ordered than the present. And the deep past, the very beginning, the Big Bang itself, must have been in a state of staggeringly low disorder, extraordinarily ordered as anything has ever been. and that is genuinely bizarre. Because we usually think of the Big Bang as chaos, an explosion, maximum violence. But it was the opposite. It was the most exquisitely ordered arrangement the universe would ever have. Everything since has been a long, slow unwinding from that initial, pristine tidiness. The physicist Roger Penrose tried to put a number on just how ordered, how special that starting point had to be, and the number he came up with is one of the most staggering figures in all of science. He estimated the odds of the universe beginning in such a low entropy state by pure chance at 1 in 10 to the power of 10 to the 123rd. Let me try to convey how absurd that number is, because you can't picture it. It's not a billion. It's not a trillion. It's not even a Google, a 1 followed by 100 zeros. It's 10 raised to a power that is itself 10 followed by 123 zeros. If you tried to write the number out in full, one digit on every particle in the observable universe, you would run out of particles. Long before you finished. It is, for all practical purposes, a statement that this should never, ever have happened by accident. And yet, the order was there. And it had to be. Because without it, nothing works. Penrose's point is that if the universe had started in a more typical, high-entropy, disordered state, it wouldn't have grown into galaxies and stars and planets. It would have collapsed into a chaotic mess of black holes. A featureless universe with no structure, no chemistry, no chance of life. The only reason there's a cosmos with things in it, with time that flows in a clear direction, with a past and a future, with room for stars to form and cool and seed the elements, is that the beginning was almost perfectly ordered. Penrose has ideas about why. His own theories try to explain it. But nothing in the known laws of physics requires the universe to have started this way. It simply did. It handed us an opening state so improbably ordered that the number describing it breaks the mind. And it's the reason the entire story, all 13.8 billion years of it, could unfold at all. Everything you've ever seen is the aftershock of the most orderly instant there has ever been. Number 1, the cosmological constant. We end with a single number, the one that, more than any other, makes physicists go quiet. It's called the cosmological constant, and it describes the energy of empty space itself. Not the energy of stars or matter, the energy of pure vacuum, of nothing. And it turns out, nothing is not nothing. Empty space has a faint energy woven into it, and that energy pushes outward, driving the expansion of the universe to accelerate. We've measured it. It's real. It's the dark energy you've heard about, and it's the dominant thing in the cosmos. Here's where it gets uncomfortable. When physicists use their best theory, quantum field theory, to calculate how much energy empty space should have, they get an answer. And the answer is catastrophically, cosmically wrong. The predicted value is larger than the measured value by something like 120 orders of magnitude. That's a 1 followed by 120 zeros. The theory overshoots reality by a factor so absurd that people call it the worst prediction in the history of physics. Not a bad prediction. The worst. Ever. Somehow the real value is fantastically, delicately tiny compared to what the math insists it should be. It's as if 120 different huge numbers all canceled each other out, almost perfectly, leaving just the faintest whisper behind. Almost, but not quite, to zero. And that whisper is everything. Because think about what happens if you turn the dial. Make the cosmological constant a bit larger and positive, and empty space pushes outward so hard that the early universe flies apart before gravity can ever pull matter into galaxies. No galaxies means no stars, no planets, no life. Make it a touch negative instead, and the pull wins, and the whole universe collapses back on itself, crushed, long before life could arise. Either way, you get nothing. A cosmos with no structure and no observers. The band of values that allows a universe like ours, a universe that expands gently enough to build galaxies but doesn't collapse, is unimaginably narrow. And our universe landed inside it, to something like 120 decimal places. Now here's the part that turns this from a physics problem into something stranger. Back in the late 1980s, the physicist Steven Weinberg made a prediction. He said, suppose the value of this constant varies from place to place, or from universe to universe. Then the only places where anyone could ever exist to measure it would be the rare places where it's small enough to allow galaxies to form. So, any observer, anywhere, would necessarily find a tiny value. Not because it has to be tiny, but because you can only be around to ask the question in the corners where it happens to be. He even used that reasoning to estimate an upper limit for the constant. And about a decade later, when we finally measured dark energy, the value came in remarkably close to Weinberg's anthropic bound. That is one of the very few times that reasoning, the idea that the universe looks the way it does, partly because we're here to look at it, actually made a testable prediction that landed. And it lands us in a strange place. Either we live in a vast multitude of universes, almost all of them dead, and we naturally find ourselves in one of the rare live ones. Or our single universe was tuned by something, or for some reason we don't understand, to a value fine enough to permit 120 decimal places of precision. Nobody knows which. It's the deepest open question in cosmology, and it hangs over everything else we've talked about tonight. The faint young sun that didn't freeze us. The moon that steadied our sky. The carbon that built us. The 1 in a billion scrap of matter that survived. All of it plays out inside a universe balanced on a number so finely poised that we can't yet say whether it's an accident, a selection, or a message. We spend our lives worrying about small things. And the whole time, the ground we're standing on, the very fact that there's a here to stand in, rests on empty space, carrying exactly the faint, impossible energy it needed to. Not too much. Not too little. Just enough for us to exist and notice how unlikely that is. Maybe we really aren't supposed to be here. Maybe every number should have come out differently and left the universe dark and empty and silent forever. But it didn't. The dice landed over and over on the one face that allows a mind to form and look up and wonder why. And that, more than any single fact, is the thing worth sitting with tonight. Thank you for watching and sticking till the end. We've got plenty more videos coming in the future. Hit that subscribe button so you don't miss them. See you in the next one.